Hello there! To understand RSA and elliptic curve cryptography, which we'll study in chapters 7 and 8, you'll need to recall some basic notions from elementary number theory. We'll review these notions in today's lecture.
The set of integers is denoted by z. We'll say that an integer a divides an integer b if there exists an integer c such that b equals c times a. For example, minus 6 divides 42, whereas 14 does not divide 105. If a is an integer and b is a positive integer, then long division of a by b yields a unique quotient q and unique remainder r, such that a equals bq plus r, where the remainder r is non-negative and strictly less than b. For example, when 73 is divided by 17, the quotient is 4, and the remainder is 5. We'll denote the remainder upon dividing a by a mod b. An integer p is said to be prime if its only positive divisors are 1 and itself. Otherwise, the integer is said to be composite. Primes are the building blocks of the integers in the sense that each integer n, at least 2, can be written as a product of prime powers. Moreover, the factorization is unique up to rearrangement of the prime factors. The prime number theorem asserts that the primes are plentiful. More precisely, let pi of x denote the number of primes between 2 and x. Then, pi of x is roughly equal to x over log of x. The greatest common divisor of integers a and b is the largest positive integer d that divides both a and b. By convention, we'll define the greatest common divisor of 0 with itself to be 0. For example, the GCD of 15 and 50 is 5. Two integers are said to be relatively prime or coprime if their GCD is 1. The GCD of a and b can be determined by first computing their prime factorizations and then multiplying together the common prime factors. For example, the prime factorization of 4,864 is 2 to the power 8 times 19. And the prime factorization of 3458 is 2 times 7 times 13 times 19. And so the GCD of the two numbers is 2 times 19, or 38. A faster way to compute greatest common divisors is the Euclidean algorithm, which was designed by Euclid around 300 BC. The Euclidean algorithm is based on the following fact. Let a and b be positive integers where a is at least as large as b. Then, the GCD of a and b is equal to the GCD of b and a modulo b. So one can compute the GCD of a and b by computing the GCD of b and the remainder r upon dividing a by b. The second GCD has smaller numbers than the first, so the problem has become a bit easier. The Euclidean algorithm uses this fact repeatedly, replacing the pair of integers ab by the pair br, where r is the remainder upon dividing a by b. Observe that the remainders form a strictly decreasing sequence of non-negative integers, and so must eventually reach 0. Hence, after the last division step, we have two integers a and 0, whose GCD is a. Here are the division steps in the Euclidean algorithm for computing the GCD of 4864 and 3458. You can observe that the remainders are strictly decreasing, and so must eventually reach 0. The GCD is the last non-zero remainder which is 38 here. Here is a fact that I won't prove. If a and b are integers, not both 0, then there exist integers x and y such that ax plus by equals the GCD of a and b. Such integers x and y, and also the GCD d, can be found using the extended Euclidean algorithm. The extended Euclidean algorithm, shown here, executes the division steps of the Euclidean algorithm. At each step, the algorithm also maintains integers x and y, such that ax plus by equals the remainder Ri in the Euclidean algorithm. I won't explain the algorithm any further. I'll next review the ring of integers modulo n. Let n be the modulus. We say that two integers a and b are congruent modulo n, if a minus b is an integer multiple of n. In other words, a minus b is divisible by n. Equivalently, a is congruent to b modulo n if a and b leave the same remainder upon division by n. The ring of integers modulo n, denoted Zn, is comprised of the integers between 0 and n minus 1, where the arithmetic operations of addition, subtraction, and multiplication are performed modulo n. For example, the set of integers modulo 17 is comprised of the integers between 0 and 16. These integers can be thought of as being arranged around a circle. In Z17, 9 plus 15 equals 7. More precisely, 9 plus 15 is 24, which leaves a remainder of 7 upon division by 17, i.e. subtracting 17 once. Similarly, 9 minus 15 is 11 in Z17, and 9 times 15 is 16 in Z17. The multiplicative inverse of an integer a modulo n is an integer x, such that a times x is congruent to 1 modulo n. Such an x might not exist. If it does, then it is unique modulo n, and a is said to be invertible modulo n. One can prove that a is invertible modulo n if, and only if, a and n are relatively prime. For example, the invertible elements of the integers modulo 9 are 1, 2, 4, 5, 7, and 8. For instance, the inverse of 4 modulo 9 is 7, since 4 times 7 is congruent to 1 modulo 9. Inverses can be computed using the extended Euclidean algorithm. Let a be an integer that is relatively prime with n, so a is invertible modulo n. Use the extended Euclidean algorithm to find integers x and y, such that ax plus ny equals 1. Now, reducing both sides of the equation modulo n yields a times x is congruent to 1 modulo n. This is because n is congruent to 0 modulo n. Thus, the inverse of a modulo n is x mod n.
We'll see in Chapter 7 that the correctness of the RSA cryptosystem relies crucially on Fermat's little theorem.
The theorem states that if p is a prime number and a is any integer not divisible by p, then a to the power p minus 1 is congruent to 1 modulo p. In other words, a to the power p minus 1 leaves a remainder of 1 upon division by p. Fermat's little theorem can be used to compute inverses modulo a prime p. Indeed, if a is an integer between 1 and p minus 1, then a is not divisible by p. So the inverse of a modulo p is a to the power p minus 2 modulo p. This is because a to the power p minus 2 times a is a to the power p minus 1, which by Fermat's little theorem is congruent to 1 modulo p.
In V6c, we'll introduce some notions from complexity theory, including the notion of a polynomial time algorithm. We will then analyze the running time complexity of algorithms for integer arithmetic and modular arithmetic, including the repeated square and multiply algorithm for modular exponentiation. See you in V6c.